Okay. Thank God I did not stream for like 30 minutes before I realized that. Um, let's see, is the desktop audio working? Just play it. Yeah, seems like it.
C.
Okay. Um, so last stream I was working on creating custom ligands for, or not really ligands, but custom residues to use in Amber and in effect Gromax as well. So um, I spent a lot of the day creating this script. Where is it? Here. So I was looking into like, uh, so basically the way to do this is to use Gaussian to get a geometry optimized structure and then feed that through antechamber so that I can read like the partial charges that Gaussian calculates and then um, add those partial charges while getting rid of the capping residues. And it's just like a whole mess. Like it takes forever to do, basically. And there's a lot of places where people can mess things up. So I wanted kind of like a more streamlined, um, routine way of doing these things. So I decided to use Sci4, which is an open source QM software akin to Gaussian. And I found out a way how to calculate partial charges for a molecule. If you give it like the mol2 file, it'll calculate those. Um, I don't really know how like accurate these calculations are. I mean, it says I'm using, B3lib, Hartree-Fock, da 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 with the correct basis set, and then do a two-stage RESP charge fitting, which is what Amber does. But TBH, I coded a lot of this with ChatGPT and just looked at the outputs, and they seemed right to me. I've also compared these computed partial charges against like um, known ones that I found on the internet for like ATP and stuff, and they're very similar, and none of the charges look extreme. So, um, nonetheless, like this is just way simpler to do than the old scheme. So, um, I did that code. It runs fine. So, what I'm working on is basically integrating these uh, thioether rings onto a peptide because that's what my enzyme catalyzes the formation of these thioether rings. And so these are like, for example, it looks like something like this here. So these are very complex, like cyclic structures that load. Hello, maybe this. There we go. So yeah, it looks like something like this. So this is where this is a cysteine residue. This is the uh, right here's the N terminus. So this would be like a cysteine, and it'll attack this dehydrated. Um, that'd be a threonine, which looks like this right here. But so when you're parameterizing these custom ligands, you got to add these capping residues here, and you have to do a constrained optimization. So you force these to be a specific charge. Together they add up to zero, so they're neutral. And then you force the charge of like the inside to be zero, and then you do restrained electrostatic potential charge fitting. And I ended up getting uh, these values here, so you can see like uh, where's trying to find like the capped charges. Here, I could do this. So C29 would be one. Where's C29? Right here. So that's the charge of C29, which is part of the like ACE group, whatever it is. Now, are those charges right? So we can look here. C29, yeah. So that's a perfect enforcement there. And all these other charges in the residue are optimized themselves. So it seems right. And it took me forever to figure this out. And then the next steps, so you got to run anti-chamber. And I could probably rope this in as part of the script, but right now it's not very hard to do by hand. You basically just run this anti-chamber command. This will give you the amber version of the charges. This literally took like, this command right here probably took like 2 hours to figure out. And really it was just specifying this as amber, which is like ridiculous. And then don't even get me started on the MC file. So this is really strange. So the MC file basically specifies atoms to remove. So you want to like basically outline like the capped atoms to get rid of here. And then you want to specify the main chain. So in a ring, there's actually like, I guess you could think of it as like 2 main chains, you know, because it's a cyclic structure. But when you write down the atoms of all of these like main chains, so like everything around here in the ring, it like messes up T-leap completely. So what I found is that if you start from the N terminus here, you have to just walk along this thioether link, and those are the only atoms it needs to basically get to the correct FRC mod file, which you can then load into T-leap and get your parameterized ligand out, right? So at this stage, we're trying to put the ring into the peptide and see what it looks like, basically. So what you need to do from here is create a mapping from these atom names to, say, like AlphaFold atom names. So that's what is on the agenda today. And then I'll simulate this and see if everything looks right. And if it does, then that's great. That really expedited the process. And for geometry optimization, I'm using the ATB Automated Topology Builder website. This uses, I think, games QM. I don't really fully understand what's going on, like, but it says it creates, you know, QM calculations to be used for like Amper and GrowMax and all these other things. So I don't know, seems legit. I see other people citing this, so. This is BOGO. This has 365 milligrams of caffeine. Every time I take a sip, my lip tingles. So we're locked. We're locked and loaded today. All right. And then another thing we have to do, so I'm working on simulating this system here. This is for a lady. She's in the computational chemistry class and she wants help with MD. So I'm setting up her simulation to help her out, and we just want to make sure that the bound and the apo are basically have the same conditions and stuff, which shouldn't be too hard to figure out. Yeah, that's what that looks like. That's in GrowMax. Right, so let's tackle this first. And I have to go around like a couple hours, so it'll be kind of a small stream. But we have our, so these are unmodified. So I already kind of laid out the mapping. Basically what you do here is Where do I want this? I want this over here. Yeah. So you make like an outfold prediction. You look at it in PyMol, and then you like select the atoms um, that you just select all the atoms around the ring, and then you select those exact same atoms along the parameterized ring, and then you can have this. So you just copy this from the output in PyMol, so you know that like an AlphaFold cysteine 46 SG needs to be renamed to S1. So that's kind of the move right there. CYS A 64 of 46. So here it's going to be S1. I'll name this to RIA. So this is going to take, a couple minutes. CB goes to C24. Yeah, but really I only have to do this once, so I can save this and then use it as a reference for later. C23 goes to, or CA goes to C23. So it's going to be kind of boring, but it needs to be done. N5, well, N goes to N5. And I'll probably, should I just write a script for this? Let's do that. I think we can one-shot a script for this pretty easy. Look at the mappings for AF atom names and ring custom residue, custom ring atom names. Okay, so I want to say my goal is to create a script that can parse this mapping. Let's see what it says. Right. Do I need to be more detailed? So each line under AF we need to find those in an input.pdb file and change that to a corresponding line under RIA. The atom name, for example, so we have this here. So CYS 46 atom name SG will change to RIA 46 S1. We will the first line under AF corresponds to first line in RIA. Note that RIA is one residue. So changing to RIA will have the same residue number as the first residue. We'll do this for all rings and output a .pdb file with the names updated. Write this code for me in full, please. Okay. Okay. So let's just stop it there. So to make the script more general, we can actually say to parse this script explicitly. You know, use mappings.txt file to parse this should be a general script for mapping or changing residue names. Maybe that'll work. Dictionary, RIA. Okay. Ugh. No CLI, please. Rewrite the script in full with global parameters or file paths, etc. All right. This is one of the scripts that I should probably learn how to code on my own, because it's kind of like an easy task to do. But nah, not yet. I will eventually. All right, so the input PDB will be this. Conda activate, let's just do Sci4. env list. Oh, file path. Python. At first glance, it might seem kind of sus. Oh wait, hold on. Let me change this back actually to the original. Yeah, so they are gonna change to 42. Okay. Yeah, I think it worked. But what we want to do is comment out those atoms within adding in asterisks. When we run tleap, we do not read those items. For example. Should turn into alright, so meantime let's make touch tleap dot in. We can go here, all rings tleap, so that's fine. Paste that there. So we need to add ATB rings like that. So our file paths are right. All right, let's try it again. Okay. Now I guess we could take a look at this and see what it looks like. Whoa. Why does it seem so far out? I mean, it kind of looks okay. I don't know why there's like an atom way out in the stratosphere. Oh, okay. So that's a problem. Um, I see. So this needs to be rid. So now let's look at it. Yeah, it's better. It actually looks good. Okay, so now let's do T-leap, see if that works. Great. Modify this T-leap script to load the output.pdb and create a .pdb what else do I need? Oh, so it'd be a parm7 and an rst7 file. Oh wait. Yeah, paste this. Okay. Good, I was smart enough to delete that. Fully modified, yeah. Alright, moment of truth. Oh. Ah, I know what it did. Yeah, a slash here. Oh, do I need a double? Does that work? Yeah. Because we're in a directory, so you go back one. 0 warnings. There we go. So this should be connected to that, which it will be. There's also a threonine residue we need to add someplace. Ring A. This is so cool. So yeah, threonine 44 needs to change. I think. Which shouldn't be hard. I wonder if we could actually do the mapping for that. This will prove if it's general or not. So we could do ZDB alpha fold. Just getting the pi mole over there. So we want unmodified sequence. So I know it is, so these are all done. That's the first ring, so it's that one here. Show sticks, hide cartoon. Okay. This is the end to C terminus. And then we need file, new window, skip. So this is kind of the move for mapping atoms together. Here, yeah. Then we can drag and drop that. So this is going to change into that. So here's what you do. You go to editing, you go boom, 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 boom. Sure, I guess we could do that one. Oops. So this would be AlphaFold. And then for ZDB, be that. So a way to make this more general, I mean, this is just for my system, you know? It's not a big deal. We could do like 48, like specify like the residues or whatever, but it's fine. All right, let's see if this works. So be that, and then we should see 48 turn into ZDB right here. Yep, perfect. Wow, I'm glad I did that because we would have been sitting here for like 40 minutes doing changing names and doing exactly this. Close that and did tleap again. Uh-oh. ZDB does not have a type. What you mean? $51. Uh-oh. Output.pdb. That's weird. Oh, it changed those residues for some reason. Huh. Okay, so now we're hitting our first snag. Something weird is happening. I think it's not picking up the so this is N2, C8, C12. Maybe because it's last? Let me put this first and see what happens. Now something real weird is happening. Well, it was almost cool. So I added CDB to change residue 48 alone, but something strange is happening now where I am getting this error. Here is the mapping.txt file. The issue is that the parser encounters CDB before seeing ring. Oh, I see. Contains. Yeah, any section header. Okay, so it was expecting a ring there. And now my session has reached its limit. It's okay, I shouldn't need it anymore. All right. So now we could maybe do tleap now. No errors. Output that would be fully modified. So then there we go. It kind of has a little bit of a tilt there, which is wrong, but probably will work itself out. Regardless, it looks properly bonded. So yeah, this needs to be connected. Those two need to be connected. And yeah. Yeah, very curious to see how this goes. It's, yeah, no. I mean, this should be flat. So unfortunately, we have to whatchamacallit, send this off to the supercomputer to run because Amber requires a license, and it seems as though the supercomputer is not working. So that's on standby, I guess. Let's check this out in Primal. Okay. There we go. Wow. Look at that. How cool. I mean, I could do something in GrowMax and run it, but think it's kind of a waste of time because I don't really need to do that. I guess we can move on to making sure the conditions are the same in GrowMax. First, let me take a baby sip of this before I have a heart attack. It's so tart. Oh, another thing I'm kind of concerned about is the C terminus of this. So this is ring D. So this is the C terminus right here. So I think we need to carboxylate it. I think you just add like an OXT atom or something. Because this wouldn't be right. That's why I think it has a -1 charge. Oh, let me do this again. Yeah, it's going to say this a lot. Yeah, -1. So I think we had an OXT. So is that possible? I guess we could have an ACE group. It's probably fine. It's probably fine. Custom residue. Let me ask ChatGPT. Oh, that's my boss today, actually. So is the N. So we need to add an enemy group. Can I just do this? Uh, 486. I don't know. Maybe it's ChatGPT. Yeah. Add an C terminus to this custom residue in Amber. Is this possible? Wait, what does lysine turn into? Is that part of Rick? It probably is. Yeah. Wait. I need to do it to here. Right, right. Some leftover wine right here. Ugh, dude, white wine is so bad, especially warm. I would never let it go to waste, though. Oh. All right, while that's going, let's check this out. So I think I make the APO simulation like the bound. So let me delete some of these files. Conda activate Amber that has Chromax on it. So this is the bound stuff. So let's look at the commands. Where are we at? Where are my notes? Notes V2, yeah. Y'all should check this guy out. Big fan. Really nice music. Okay. Our neutral cap, another peptide-like residue. Here are 2 reliable recipes. Okay. Yeah, I was thinking enemy. I don't want to build the chain. Why can't we just add an enemy to the end? I know how to do that actually. We're gonna go here, there. We'll look at this there. So we'll just copy this. Yeah. And I don't think we have to put in the coordinates. Ugh. So I was thinking of doing fully modified, or not, it'd be this. And just plopping that in there. Maybe we could get away with just doing this little thing. No. We're not going to do it to there. We're going to do it to the output. We're going to do it here. All right, let's see if Amber gets unhappy with this. So that's wrong. So this could be at least be named 66, or no, 63. And then we can just delete this crap. Let's see what it does. Okay, I think it worked. Do we have an enemy group? Yes, we do. Is it off the deep end somewhere? Yes, it is. So we don't need a tur. So it just puts it at the origin. I think ChatGPT can probably do this. So let's just modify the .pdb file and add the. I mean, can I do this in Pymol? I feel like I can. Was it like wizard mutagenesis protein? Okay. Encap pseudo. I don't know. I think we're just gonna have to have ChatGPT do it. So let's just modify the PDB file and add the enemy cap residue. Here is an example. Here is the structure. To add it to. I feel like there's probably a simpler way to do this with tleap maybe. Like, can you add like a I don't know. Yeah, put it. Let's see what it says. It's an amino group, right? Pretty sure. Carbonyl C7. There's got to be a way to do it in tleap. Maybe like So you can do that. Dataset connect. What? This is PP trash. So it's just building a PDB. All right, let's see how this does. Get the number right. Let me see. $52 does not have a type. So let's just get rid of these. All right, I'll see what this is. Where's the enemy group? It's there. Am I missing something? All right, let's look at the structure again. Maybe I clicked the wrong thing. Oh, there it is. Yeah, it's in there. All right, let me ask a simpler question. How do I cap the .pdb off with an enemy group? I want to give it this. And tleap. I'll check my email right quick. Okay, we have to leave at 1. Yeah. Okay. All right, we're good. Add PDB res map? Is that a command? Oh, I knew there was something. What? What is this? Ooh. That's cool. Both of these ways worked, and I end up doing eventually. Use clear. I think the rose map should have it. It's strange. Maybe amber already just does this. It's not standard chemical term. Like, do you not have to parameterize those? Let's do. What? I wonder if my way's okay. So they're talking about disulfide bonds, which is a little different. I don't know. I think my way kind of works. Yeah, the only issue would be like if it was like a huge cyclic peptide. Like you couldn't like geometry optimize that and get the charges, but you might could do like the first. I don't know what to do actually. Or something like that. Yeah, I want to keep the coordinates. If manually add, so I think this would be the move. Let's see. Oh. Okay, never mind. Not that one. Maybe this one? Get rid of that. Nah, I just added it to the very end over here. I want to connect them. Is that what it did? Did it add this? Oh, yeah. I know that's not gonna work. Rip. Actually, I have an idea. Wait. Do I have an idea? Okay, I think this could work. So we're gonna have to do it the old-fashioned way. Drag that in. So we are going to take that. Maybe, okay, hold on. Whoa, 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 whoa. Get rid of the wizard. Done. Select this. And then we are going to maneuver this bad boy over here. See what I'm doing? Center, selected. Okay, so we basically, where are we? Okay, so that's going to connect there. Wait, no, that's going to connect there. That's going to connect there. Okay. Let's just see. Align AA selected. Ooh, that works. Okay, so we need to change the coordinates a little bit. It's kind of on the money though. So let's see. Select that, edit. Yeah, That's about right. Yeah, that's good enough. All right, so now I think we could just print the coordinates of this. So there's a way to do that. To define it as like an X, Y, Z or something. Yeah. Print X, Y, Z. Okay. Sweet. And then basically do that. Those coordinates look right too. Oh, this is on the fully modified, so I gotta change this. Scoop that. Put it on output. Yeah. All right. I think it works. Yeah. There we go. Yeah. Looks good. It's a little bit off, but what we could probably do, actually, is get rid of these hydrogens. Like, don't specify the coordinates of those. Really, all we need, I think, is the nitrogen alone, honestly. I thought it could build itself, maybe not. We'll do this. Okay, why are you doing that? I mean, this looks good. What is this, though? Is the tea leaf still whack? Yeah, that's why. There we go. Yeah. The hydrogen is just a little bit farther than it should be, but that's because of the decimal places that we deleted. So it'll be all right. I've seen worse, especially like these sulfur atoms, like they're way far off. But hopefully it'll work itself out. But we won't know until we simulate it. Why? Why doesn't it work, dude? Maybe maintenance. All right. Let's see where we're at. All right, so how do I want to approach this? I think we just basically do this. If we run the box size should probably be the same. The only difference is we're adding constraints on some atoms. And it might just end up being the same thing. Like, so let me ask ChatGPT real fast. The system. How would I do this so that what would I need to ensure? I mean, I already kind of know. So this is APO, right? Yeah, that's APO. This is bound. Time step is the same. I mean, this one has TC groups too. No, I think they're identical. I think it's probably fine. So this is what this simulation looks like for the bound. This is for the APO. So one's in that and the other one's in that. I like the way this looks. I think I just run this back, and I also like the spacing here. I'm kind of concerned about this. But I think someone in the tutorial talks about how not to worry about that. I think it'll be the same thing. As long as the temperatures and pressures are the same, it should be fine. Let's just do it. I'm being lazy. Okay, this shouldn't take very long anyway. All right, so let's look at the notes here. Let's look at the notes here. So we take the alpha structure, process the grow to pol.top, DAPO. So so we're going back a directory. All right, we can just copy, paste into there, and then change the notes just so it's simpler. Boom, boom. Positional restraints ITP. We have the same water. And we choose 6 here instead of 1. So that's honestly kind of a big difference now I think about it. So that'd be 6. Okay. Add coordinates. Yeah. Edit conf, new box. So we'll do that. So we want dodecahedron. Change it to that. Okay, so let's check this out. The new box. Okay, it's just a box. We're not going to see anything. Solvate. Doing that. Get rid of that. Get rid of that. Get rid of this. Doc's right. So we need to change to pol.top for a second. Just for APA. Okay, I guess that's fine. Step 3. To pol.top. So now we're going to add our solvent molecules. 7575. Still looks like a box. And this is the ions.mdp, so let's make sure these are the same. Here. Yeah, they look identical. So we can move on with that. So it looks fine. Okay. And then we do gen ion, neutral. Yeah, all that looks fine. And then we pick the sol, which is 13. Okay, so now we do EMSD. Do we have that? Yes, we do. No, only in here actually. EMSD.mdp. There we go. So let's check this one out. I'm just gonna touch em_sd.mdp. So it's steep descent, energy minimization. All right, so we can copy this, put it in notes. See how this goes. Solve ions.grow. So we want this. And so that should be good. We want to do that. So then we copy over the EMCG MDP. I think we can go directly from here. Yeah, into that. Nice. Okay. So now they're making an index for the ATP and the AMP. We don't need to do this stuff. And they're adding the ligands. Yeah, we don't need to do that stuff. So let's look at the, so we can get rid of that. Let's see how the NVT file compares. NVT.mdp, look over here, NVT.mdp. Looks very similar. So we could just change the TC groups to this basically and copy that over, I believe. So we'll change this to protein. And was it non-protein? Let's see if that works. Oh, get rid of that. NVT.mdp was nothing. It's right here. In the list of index groups. Okay. Maybe I spelled it wrong. Oh, there we go. Nice. So that might take a second. In the meantime, we'll just copy the rest of these here. Change NPT. NPT. And then go. Boom, boom. Okay. And then we'll do the same for the MD. MD. Back here. Copy that. Paste that. There we go. All right. Now we should be consistent with the bound. The only difference is the ligands. Let's look at the topol at the top. 3 sodiums, that much solvent. What about here? 7 sodiums. That's because of the ATP and AMP. Together, that's like -5, I think. 3, 4, yeah. So that makes sense. There's also a magnesium in there. So I need to double check and see if that's right, actually. If the thing is neutral. Damn, this took forever. We're at NBT. It's probably some streaming. Yeah, I'm probably going to have to do this later. See how it looks though. It doesn't look slanted. Wait, I think we actually need to look at this. Ah, there we go. Yeah, it's slanted. Nice. Okay. What else can I do? That's pretty much it. I could work on the model. What would I do though? Anybody else want to see me do something? Could read papers. I think I need to figure out what I present actually. Oh, I hope it's not next week. If it is, then we're gonna have to do a lit review. I think mine's actually coming up. Let's see, October 27th. Let's go. That is next week. But it might have gotten pushed back. And it's lit review. So I gotta start finding some papers. I think I already have a bunch in mind. Oh, I just got done. Never attribute to malice what we can adequately explain by stupidity. Words to live by. Gromac's got some banger quotes. All right, so let's just take a gander at the NVT. This would be XTC. So it's just the water's moving. The protein's jiggling a little bit. This never gets old, honestly. Crazy your computer can make stuff like this. So what we would hope to see is this open. I guess that's one thing I can begin to work on is like figuring out how to, I mean, I've already kind of done that. Just create protein contact maps. Just not a hard thing to do. But if you do that, you can take the difference between the two protein contact maps and then get an idea of what are the differences between contacts and the trajectories. Or you could do like simple RMSD stuff, you know. But this one here I've ran for like 100 nanoseconds. Maybe 50 nanoseconds. That's gonna rubber band, I think. Yeah. is it? No, it's coloring. New cartoon. Res name, AMP, ETP, and G. We can show these as van der Waals. Whoops. Yep. There they are, right there. So hopefully in here, the structure will stay closed. We would see like a phosphate transfer, but we can't really model that. We could do cool stuff like color by secondary structure. So we have this beta sheet, helixes, looks nice. I guess we can go to the next step here. So what is that? 2 hours? Yeah. I think I'll call it here. I got a meeting at 1, so. All right. Peace out.